All right, so welcome everyone to another StaPH-B call. I'm really excited to welcome everybody to October's call because we have a few different speakers on today, and I'm not sure that it's going to take the full hour, but I figure leaving some room at the end for a little bit of discussion and a little bit of kind of talking about where we're headed in this particular field is probably a good idea on this call. And collectively using a little bit of the hive mind to talk about where people are at and just kind of like talk about our experiences so far with this particular pathogen. I think are going to be really useful and really needed. As I was saying kind of before, for those of you who joined the call early, we have a really well attended call today, and it's partly because of our growing membership and our continued, sustainment of people who want to be on these calls. And so I really am truly humbled by how much this particular community of people has grown over the past, 6 years since it's been kind of in existence. It's been tremendously successful, I think, in terms of the people who participate and who join these calls and then, talk in the Slack channels afterwards. And so I really wanted to say, thank you to all of you for being here, because it's because of this community that, StaPH-B really exists and continues to thrive. So a couple of just, the housekeeping features as we go forward. So I'm going to be monitoring the waiting room just to make sure that anybody who is still in there gets admitted to the call. If there's anybody who you know of who may be having difficulty joining the call, please try to let me know, maybe in the chat feature, and I'll try to make sure that they can get on. And I think that everybody should be muted as they come into the room, but just as always, if you notice that your mic is on, please try to mute yourself. And if not, then I may have to come by and mute you manually. But we haven't really had that problem because I think you guys are all fantastic. So with that, I think I am going to go ahead and introduce our speakers. So we have a couple of different speakers today, like I mentioned. We have Chantal Vogels and Nick Chen from the Grubau Lab, who are going to be talking about primer design for monkeypox. And they're going to be kind of updating on their progress. I think that they have given some fantastic talks. If you were on the symposium for the monkeypox kind of event that was put on by BVBRC a couple weeks ago, I know that there was some fantastic information and updates that were given there, and so we're really excited to have them on this call. I've got Kevin Libuit from Theogen, who's going to be giving some updates on kind of some of the bioinformatics that they have developed for their kind of use cases. And I've also got Erin Young from Utah, who's going to be giving some updates to the secret pipeline and how that is being used for monkeypox sequencing as well. And so I think with that, I'm going to turn it over to Chantal and Nick, and I'm going to mute myself. So take it away, you guys, and thank you so much for being on the call.
Thank you, Logan. I'll start the presentation, and I'm basically going to start off by giving a little bit of the broader background around amplicon-based sequencing, and then Nick will take over to really dive into the monkeypox specific primer design and validation that we've been doing. And it's actually really great to see that there's a lot of our collaborators on this call. So really great to see everyone on this call. And I'm really excited to be sharing these results that we've gathered over the last months. So I'll start with a bit of a disclaimer. We can go to the next slide for that. I'm actually a arbovirologist. So normally I study mosquitoes and the viruses that they transmit. So I'm not an expert in DNA viruses. All the viruses that I studied so far are RNA viruses. So we're dealing with a slightly different beast here. So I just want to put that out as a disclaimer here. And I'm going to use that also as a bridge into the sequencing approach that we developed. What we use a lot with the arboviruses that we sequence is amplicon-based sequencing. And this was initially developed for Zika virus. But to kind of put this in perspective, with metagenomic sequencing, you basically sequence any nucleic acid in your sample. That's great if you don't have any upfront information on what you're looking for. So if you're screening for a novel pathogen, there's some strategies for enrichment or depletion, but in general, there's like no direct amplification of your nucleic acid. So you need a decent amount of nucleic acid to make that successful. In contrast to that is amplicon-based sequencing, where you're actually looking for something very specific. So you specifically design primers to target whatever pathogen you're looking for. So it's incredibly specific, and you amplify your nucleic acid. So it gives a much better sensitivity for detection. So if we go to the next slide, then basically, as I said, this was developed during the Zika virus epidemic. And the big challenge there was that clinical samples had very low amounts of nucleic acid and virus in them. They were typically degraded. So it was really hard to use metagenomics to get complete genomes out of these samples. So then Josh Quick and colleagues developed amplicon-based sequencing, also called primal-seq, where basically you have these overlapping amplicons that span the entire genome. So basically just designing these primer sets as a strategy to make sure that you get complete genomes. You need to amplify these in two separate reactions to basically make sure that you don't get any truncated amplicons. And that has worked well for Zika. And if we go to the next slide, it's been basically used for lots of different viruses. Again, with my experience, I've done a lot of Zika virus sequencing, West Nile virus sequencing, like really focusing on the arboviruses, but it has also been used for Lassa virus. It really gained traction during the SARS-CoV-2 pandemic. It's been basically the main way of sequencing that has been used. And that's also how our lab really got into the SARS-CoV-2 sequencing. So that's on the next slide. Where really we started investing in this infrastructure and really establishing a genomic surveillance initiative. And basically we established local partnerships with the hospital to get samples. And then in our lab, we would do RNA extractions, PCR, library prep. We sequenced at our genomic score. And basically we kind of went through this whole process. We established bioinformatic pipelines, leading to about 20,000 SARS-CoV-2 genomes, which is really huge in comparison to what we've done in the past. And what we learned here is that it basically doesn't really matter which virus you're sequencing, because you just swap out the primers, you adapt your bioinformatic pipelines, and you can basically use the same workflow for a variety of viruses and pathogens. And that is kind of that drew us into monkeypox. When we saw the monkeypox outbreak happening at a global scale, we immediately thought to ourselves, okay, let's develop primers for monkeypox so that we can basically utilize all that infrastructure that's out there by basically making quick changes so that all these labs out there can keep on sequencing, can expand their portfolios. And that I'm going to use as my bridge to hand it over to Nick. So Nick Chen is a MPH student in our lab. He's actually done a lot of this SARS-CoV-2 genomic surveillance that we've been doing, and then immediately helped us out with the monkeypox development and validation. So I really like to give him the stage to talk about all the exciting work that he has done.
Thanks, Chantal. Following up with Chantal's disclaimer, she's an expert in arboviruses. As a graduate student, I'm an expert in nothing, but I'll do my best to kind of portray this project in the best light I can. The slides will continue. Awesome. So going on the project itself, we designed a primer scheme consisting of 163 primer pairs that generated amplicons of about 2,000 base pairs in length. And when we started this project in late May, we didn't have this abundance of these high quality outbreak genomes we see over here to the right. And so because of that, we used the most recent high quality genome we had access to, which was from a UK 2018 case that would fall under the A1 lineage by the most recent naming conventions. And we went into this project with the goal of making the integration into all of the existing SARS-CoV-2 workflows as seamless as possible, but there were some changes that, of course, had to be made. Namely, because it's a DNA virus, there wasn't really need for that cDNA synthesis step, which in some ways is a benefit. Another change we had to make was adding a second cleanup step. So for the normal COVID-seq protocol, you only have one cleanup step, and that's largely because the amplicons generated for SARS-CoV-2 are about 400 base pairs in length. After tagmentation, they're a bit shorter. So that first cleanup is really just to remove all of the fragments that are well below the desired 300 base pair size. Because the amplicons for monkeypox are so much larger, we had to add a second cleanup that would target fragments that are well above that 300 size that we're looking for. And both of these changes are reflected in our protocol.io. But in terms of the bioinformatics, the only real changes that need to be made were updating the reference genome, updating the bed file that goes along with it, and updating the expected genome. Now, going to this project, one thing we really wanted to investigate was how this amplicon-based sequencing was going to perform against metagenomic sequencing. Early in the outbreak, the monkeypox outbreak, metagenomics was used for a lot of the early case sequencing, but there was some concerns that it wouldn't perform as well with samples that had a high CT value or a low viral DNA concentration. And so we partnered up with our friends over at the Massachusetts State Public Health Lab, who ran our amplicon-based sequencing primers and protocol in parallel with their metagenomic sequencing for 10 clinical samples, lesion swabs, I believe. And so that's what we can see here with the genome coverage at 10x by the CT value. And so when we look at these samples on the far left that had a fairly low CT value, so a high viral load, we see more or less comparable performance between amplicon sequencing and metagenomics. However, as that CT value starts to rise, we see a much steeper drop-off with metagenomics in comparison to amplicon sequencing. I'll be using my mouse here, or else it looks like I'm just kind of talking to no one. And so this was a really initially promising start to show that this might have some advantages over metagenomic sequencing. We wanted to get this protocol and primers into as many different hands as possible to see how it would hold up in different settings with different inputs. And so that became the multi-site validation part of our study, which the first part was just releasing our protocol into protocols.io, and we publicized that in social media in combination with just a Google form for people to request primer aliquots from our lab. And within just a couple of weeks, we had over 35 labs across the world requesting primer pool aliquots. Of those, we had 12 labs that agreed to share validation data. And we can see those on the map to the right. And of these labs, we had reflected 2 different sequencing platforms in the form of Illumina, as well as Oxford Nanopore Technologies, as well as 2 different types of samples, being lesion swabs and oropharyngeal swabs. Now, focusing first on just the lesion swabs that were sequenced on the Illumina platform, here we have all 8 labs who use that combination. And for the most part, we see a very consistent high coverage of more than 80% for samples that had a CT value of below about 29 or so. And for each of these labs, we fitted just a logistic regression, and that dashed line corresponds to the 80% cutoff value. Of course, for some of the labs, we weren't able to fit that 80% cutoff just because the samples, the data didn't range in coverage enough to fit it. But if we look at the individual labs, we see a little bit of variation in that CT value corresponding to that 80% cutoff, but really for the most part, it's fairly consistent. And in overall behavior, we see very high coverage that really only starts to drop off around that 29 to maybe about 32 CT value range. Now, another aspect we wanted to investigate was the use of oropharyngeal swabs. For monkeypox, lesion swabs tend to be the standard sample type. But I'm sure as many of you are aware, with the current outbreak, we're seeing a atypical clinical presentation where lesions might be smaller, fewer in number, or maybe even absent entirely. So having another type of, another sample type really expands the testing and sequencing. But there were some concerns that because lesion swabs are kind of pockets of high viral DNA concentration, oropharyngeal swabs might not perform as well. And so we had 2 labs that investigated oropharyngeal swabs in addition to lesion swabs, being Massachusetts and INSA. And while we weren't able to fit a logistic regression for either of them, just because of how this data is kind of scattered, if you look at the individual points, we can see that they line up very consistently with the lesion swabs. If we look at Massachusetts in particular, they used both oropharyngeal swabs in the presence and in the absence of lesions. And what that basically just means is when they were taking their oropharyngeal swab, was there a lesion in the oropharynx or not? And we can see with both of those sample types, really pretty comparable performance with all three of those sample types. So that's a good indication. I mean, the sample size for these is somewhat on the small side, but it's a good indication that oropharyngeal swabs might present an alternative sample type. Now, in addition to changing the sample type, we wanted to see how changing the sequencing platform would affect our coverage. And so we had two labs that used ONT, and they specifically used the ONT GridION for their sequencing. Starting with Johns Hopkins down here. The data kind of precludes the use of the logistic regression line here as well, but we do see some high coverage samples here right around a CT value of 18 or so. But if we look at NHS Lothian in particular, what they did was they ran their samples in parallel on both the Illumina and the ONT. I believe the Illumina was a MiSeq compared to the ONT GridION. And here we see really pretty comparable performance across both sequencing platforms. If you look at the regression line, they kind of oscillate back and forth. And these 80% cutoff CT values are just about within one CT value of each other. So we see really a more or less comparable genome coverage for these samples, regardless of which platform you're using. And while this is only just the one lab, it's a fairly decent sample number. And it also provides indication that you have a flexibility in the sequencing platform you use. Now, one question we had come up pretty frequently from the labs we were working with throughout this process was the number of dedicated reads they should be giving to their libraries. And when we did our sequencing, we were maybe a bit spoiled that we had access to a NovaSeq and we could just throw like 12 or 14 million reads per library, but we understand that's not exactly practical for everybody. And so what we did was we took the samples that we sequenced in-house and we downsampled them to 4 different read depths over here on the right, being 2 million, 1.5 million, 1 million, and 0.5 million. And so immediately visually, you can see that by downsampling that read depth, it does make a difference on genome coverage. However, if we kind of quantify that, between the 0.5 million and the 2 million reads per library, we see it between a 0 and a 26.1% difference, depending on what CT value we're comparing. However, if we look at 1 million and 2 million reads, we only see about a 2% difference. So this suggests that above 1 million reads, you start to see some pretty quickly diminishing returns. And that helped to inform our recommendations for generating at least 1 million reads per library to achieve this high level of coverage. Now, one thing we also wanted to look at was the role of both the CT value as well as the depth of coverage. And so what we did here was we broke those 4 read depths into 4 separate heat maps here from 0.5 million to 2 million. And with these, each row corresponds to one of our samples from the previous slide, with these being chosen to space it out more or less equal intervals of CT value across the entire range of CTs we saw. And so from looking at least, and the columns here are the specific amplicons that stretch the entire length of the genome. And so what we can see here is that both CT and the read depth do play a difference. If we look at the highest CT value of 35.2 here, really doesn't matter at what read depth you're working with, you're going to see pretty poor coverage in general. And with the lowest read depth of coverage, we see in general lower coverage that also does kind of transition throughout the CT values. But maybe more importantly, we see with these lower CT values across all 4 read depths, really minimal dropouts. And specifically what we found was that for all of these low CT samples of, again, about below 29 or so, only 2 amplicons, 75 and 188, were consistently dropping out with a coverage of less than 10. And when we further looked into this, we found this was not, in fact, due to mismatches in the primers. And so we believe that is just variation in PCR efficiency of the different primer pairs. And so now moving on, just a few limitations of our project here. First of all, the primer scheme specifically targets clade 2B, so that encompasses all of the outbreak samples, as well as the one we use for our reference genome. But if you were to use this primer scheme for samples or genomes belonging to different clades, you would probably get some lower coverage. This would be especially the case if you use it from the Congo Basin clades. A second limitation, the PCR efficiency is not optimally balanced between all 163 primer pairs, and that gets to what we saw in the previous heat maps of those two amplicons dropping out. And it does just result in different levels of coverage across the genome for different amplicons. Finally, the monkeypox genome has what are referred to as inverted terminal repeats, which I'm sure many of you are familiar with. It's essentially just parts of the genome on either end that are duplicated, but as the name would imply, inverted. And this kind of presents a couple different challenges. First of all, it makes it so that the primers will bind to multiple parts because these regions of the genome are duplicated. And the second aspect of that that's challenging is it makes it a bit hard to then map the reads for it. There have been some different suggestions of how best to approach this, from masking one of the ITRs to just kind of rolling with it. But it does present a challenge nonetheless. Not last. Finally, with the last limitation here is genomic rearrangements. Because this is based off of a reference genome, if we were to see significant genomic changes, those would not necessarily be reflected in amplicon-based sequencing. And so to compensate for that, we would suggest performing periodic long-read metagenomics from time to time, just to catch if any mutations were to arise, or if you could start seeing gaps in your genome, just to provide more comprehensive genomic surveillance. So in conclusion, amplicon-based sequencing provides a cost-effective and widely applicable alternative to metagenomic sequencing for human monkeypox virus surveillance. Our recommendations are to utilize existing amplicon-based sequencing infrastructure, to prioritize samples with a CT of less than 29 if prioritizing is necessary due to limited resources, and finally, to generate at least 1 million reads per library if possible. Finally, we'd just like to thank all of our partners on this. This has been an incredibly collaborative effort, and none of this would have been possible without all the individuals you see here across all of these different wonderful public health agencies. And I think with that, we will go ahead and open it up for questions. Oops.
So we can either do questions now, or I might suggest that maybe we hold the questions to the end, just so that I can make sure that we get to all the rest of the speakers. And then, yeah, if you guys are okay with that. All right. So yeah, maybe let's move on to Kevin next, and then everyone who has questions, hold on to them, write them down, and we'll ask them later.
Yeah, sure. Thank you, Logan. Thank you, Chantal. Thank you, Nick. It's a heck of a master's project, man. Very well articulated. That was great. So the perspective I'm going to be giving is, again, focus on monkeypox here, but with respect to how we've leveraged a lot of the lessons we've learned through COVID-19 and to being able to apply those lessons in the face of an emerging pathogen. And again, as Logan mentioned, this is a talk that is largely based off what I gave at the BVBRC mini symposium. We put that in the chat. Incredible mini symposium. I know I learned a ton from really a lot of the major players in our field. So definitely worth checking out. It was cool to be a part of something like that. So to kind of frame this and looking at the lessons learned through COVID-19, as definitely worth saying, this is by no means a comprehensive list here, but some of the key things we've learned with respect to public health bioinformatics, or rather just pathogen genomics in the public health space during the COVID-19 pandemic was, the utility in these amplicon sequencing protocols, as Chantal really laid out beautifully there, and that there's these really robust wet lab protocols that could be really quickly applied to a variety of different pathogens or viruses. And there is at least some framework of a best practice towards genomic analysis. Of course, there's always nuance, and this is the community where we can talk about all the nuances. But in general, mapping to a reference genome, removing those primer reads, not inheriting the reference genome into the consensus assembly these types of things. And so at Theogen, like at this point, when we saw a laboratory sort of gain these capabilities of generating these data, the major challenge there at that point, especially a couple of months at the onset of the COVID-19 pandemic, was then distributing these bioinformatics capabilities. And over the past 18 months or so, we've really seen different models emerge in how to distribute bioinformatics solutions. And I think the ones that has really landed is the use of these open source containerized workflows that are then made accessible through some kind of graphic user interface. And ideally, if there's some sort of cloud backend. And again, this is something that we've seen kind of come to fruition in a number of different iterations. I see some of the Lano folks on here. So for example, Edge is really a great example of something like that. The Gen Epi CZID resource, even things like NextStrain or the Pangolin software and Nextclade, all those being made accessible through some sort of graphic user interface and web application. And so what this has done is really allowed for this kind of model practitioner-led research and development, where we're handing these tools to the public health laboratory scientists directly, and we get this incredible community that offers feedback for rapid improvements that are optimized for the public health community. And so again, another iteration of this kind of model that we've really leaned on our team is the use of this Terra platform. It's a web application that's developed and sustained by the Broad Institute of MIT and Harvard. And again, what it is this cloud-based GUI application that connects open source bioinformatics workflows with cloud compute resource and has a user interface that's geared toward the bench lab scientists. So what we did throughout the COVID-19 pandemic in addressing that emerging pathogen was we tried to capture those best practices for generating and characterizing SARS-CoV-2 genomes into a workflow we called TheaCode. And we made this then accessible on the Terra platform. And so that all the different public health laboratories that were looking to bring up these capabilities, there was a sort of lower barrier to access the bioinformatics best practices that were being defined in more the academic or research spaces there. So in a partnership with the Broad and also the CDC, over the past year, the CDC Office of Advanced Molecular Detection supported Terra access to any US public health laboratory for SARS-CoV-2 genomic characterization. So in that, we saw really rapid adoption, especially in laboratories who didn't have bioinformatics capabilities coming into the pandemic, or at least nothing that could necessarily support SARS-CoV-2 genomic characterization. And this led to really widespread adoption that was amazing to see across various states, not only the state level, but also a ton of local public health laboratories who were even sequencing data for their first time, could in hand then start analyzing these data with the same best practices as all the other laboratories around the world. And what this did, in line with the spirit of StaPH-B, is create a community of public health laboratorians who can provide, that critical feedback to, again, further guide our development priorities to how to increase the value add to laboratories that needed these kinds of technologies. And so again, the major lessons we had from COVID-19, not in any way comprehensive, was the utility of these amplicon sequencing protocols, and then this incredible model that we've landed upon in terms of development and distribution of bioinformatics solutions. So in responding to emerging pathogens like monkeypox, as Chantal and Nick highlighted, we could adopt a lot of those same lessons. We can build and develop a wet lab protocol that's really mimicking the same approaches that were taken by the Arctic network for Zika, for Ebola, for SARS-CoV-2. Now we can take that same approach, use the primal seq, identify the high affinity primers, and distribute a wet lab protocol. So this is something we got tied into in a collaborative effort that was really, at least, corralled by the Massachusetts Department of Health here, where we were able to take that wet lab protocol that Chantal and Nick had just spoken about there, and then on our end, our task was to develop and distribute the bioinformatics resources to make sense of these data. And all along the way, the Broad Institute viral experts, they were helping out to validate the thing at each step there. So our approach in this, in that knowing that we had already had the success with this TheaCode workflow for creating this consensus genome assembly and then characterizing things, our approach was, can we, because it's such a similar wet lab approach, can we utilize the same dry lab approach? Can we take that same consensus genome assembly in terms of mapping to a reference, variant calling, and then sort of bypass anything that's pangolin specific and instead feed that assembly into the monkeypox specific characterization? So that's and also with a key priority to ensure that any kind of modification we've made to TheaCode didn't in any way disrupt the folks that were using this for SARS-CoV-2 characterization. So this is what it kind of looked like. We took the TheaCode workflow that we had for SARS-CoV-2, and instead of funneling this assembly directly into SARS-CoV-2 characterization, we simply put a fork in the road. And I think Erin is probably going to talk about a really similar process with secret. So, this isn't necessarily the secret sauce. This was just what made the most sense of how do we make this amenable to the other viruses that will, continuously be sequenced using these kinds of protocols. So that fork in the road, we were able to split it. And then for laboratories that were using it for SARS-CoV-2, it would look nearly exactly the same. But for the laboratories that were starting to adopt sequencing protocols for monkeypox, then we included the very monkeypox specific characterization resources. And again, the parallels between the wet lab and dry lab are really incredible here because, as Chantal said, you could really apply this to any virus. So now at this point, we've not only limited it to SARS-CoV-2 and monkeypox, but we've been starting to work with other laboratories, both domestically and the international community, in making this amenable to viral genomic characterization sort of at large. So we have a number of different viral pathogens that will enable characterization. So I know this is a figure from Frank Ambrosio's upcoming poster at ASM NGS, where he'll highlight his work in this, in making this same TheaCode workflow amenable to HIV characterization. There's a couple of folks on this call, for example, I know Byong in New Jersey Public Health Lab has also used TheaCode for West Nile virus characterization, or at least assembly, and same with Massachusetts Department of Health. And even in the face of the current surge of Ebola cases, you can see this being applied in exactly the same way. So long as those user-defined parameters for the primer bed file and the reference file are provided, we can take the same approach of creating those consensus assemblies. And then the task from there is figuring out exactly how we want to characterize once we have that consensus assembly. And again, leaning on the progress we've done with COVID-19, I think the timeline to getting access to these resources on the Terra platform for public health labs, for SARS-CoV-2, I think it was somewhere like 3 months or so it took us to really hash out the workflow and get it on Terra and make it available to laboratories that we were initially working with. And then another 18 months or so to see the sort of adoption you've seen, or that I've kind of got imaged here. But with monkeypox, it was just a matter of weeks for us to really work with Chantal's group and figure out how do we get this, amenable or TheaCode amenable to monkeypox. And this same group of practitioners also have immediate access to this workflow. So this has been really cool to see. We worked most closely with the Massachusetts Department of Health, but I think Los Angeles County was a laboratory that originally reached out to the Grubal lab and got the primers, and they already had access to these workflows for SARS-CoV-2. So it was a relatively quick path for them to have the same analytical workflow available to them for monkeypox characterization. And so what we've done in this spirit, again, of StaPH-B is making everything as open source and available and as accessible as possible. So all the source code is available on GitHub with open source licensing. We use as many of the StaPH-B Docker images as was really feasibly possible. And then even working with the Broad folks and the Terra developers to get a featured workspace to further ease the adoption of this particular resource. So in a couple minutes, I can kind of highlight what this looks like for folks that are interested in the Terra side of things. But this is the featured workspace that is publicly available to anybody currently, and you can even clone this and start utilizing this at this point right now. We've tried to document this as detailed as we possibly could. So even if you care to use this today, this is a workflow that we make for the public health community. I will say for the US public health laboratories, that AMD funding to support Terra workspaces for SARS-CoV-2 can also be applied to monkeypox. So if this is something you're interested into getting set up, feel free to reach out to us. But basically, once the data, we pre-populated this workspace with some of the monkeypox data that LA County had generated, some of which has been analyzed to show what these results will look like, some of which we encourage folks to analyze using the step-by-step instructions that we lay out there. But in this framework, again, there's a graphic user interface for interacting with the bioinformatic software. You have this data table layout of all your results. If you care to run the analysis, it's kind of a click button interface where you identify your workflow, you select your inputs, define your outputs, and hit run analysis. And then you're given these kinds of results on the back end there. All right, so with that, again, the major takeaways I really care to impress in this talk is that incredible lessons have been learned throughout COVID-19 especially in the public health bioinformatics space, not only in these crazy collaborations that are happening internationally, wildly dynamic, but also with respect to the utility of these amplicon sequencing protocols. As I mentioned, there's other emerging viral pathogens where this makes sense. Where, I think we're getting looped into other conversations with Grubal Lab and malaria, and this also lending itself to utility in that case as well. And then this really incredible model for distribution, development and distribution, kind of a meeting point for bioinformatics resources to the entire public health community. And all these resources are currently available, as I said, some of which can even be supported by OAMD Terra workspaces, if this is something you're interested in. And then the last thing I want to highlight, the model for development and distribution is not specific to amplicon sequencing. It obviously lends itself well here in monkeypox, but this is also a model we're kind of taking and starting to utilize in all the other pathogens that we once used our time to focus on, all the enteric pathogens, nosocomials, TB, and kind of everything under that umbrella. So with that, again, similar to Nick and Chantal, it's thanks to the community. Obviously, our work working with the Grubal Lab, Massachusetts, and Broad, but the entire StaPH-B community, Spheres, Phage, the Terra developers, and I'm representing a group of incredible and dedicated public health scientists in Theogen. And then what's also great now too is I can give a huge credit to the different public health laboratories that provide us with this feedback for how to develop and optimize these resources for this community. And then also I like to end on this side too, because this is StaPH-B being a domestic focus here, but we also have great partnerships with APHL Global Health, where we're taking this same model and making these resources available to the entire global public health community, because that's also a major lesson we've learned here, is that the public health community is a collective us, and we all need to ensure that we have these capabilities to perform the pathogen surveillance required for informed public health decision making. So with that, I will take questions at the end of Erin's talk. Thanks, Logan.
Thank you, Kevin. All right, so yeah, let's go ahead and give Erin some time now. I want to make sure that we get to her and make sure that we get all the presentations in, and then we will go ahead and take questions. So Erin, if you want to go ahead and share your screen and give us your updates, the floor is yours.
Awesome. All right. Secret is named after a place, and the workflow was initially for SARS-CoV-2 sequencing, but as iterated in Kevin's talk about TheaCov, a lot of the same principles for SARS-CoV-2 sequencing and consensus generation can be applied to monkeypox. Because monkeypox, even though it's much larger than SARS-CoV-2, it's still a considerably small genome, and we're still mapping it to a reference. And so there's a lot of similarities between the two, but similar to TheaCov, there is a org for monkeypox sequencing. So right now, there is a profile in Secret for monkeypox. This was developed for the monkeypox sequencing that we were initially doing, which wasn't amplicon based, it's just metagenomic. And so metagenomic doesn't need any kind of primer trimming. So many of the aspects of the workflow were still needed. We still needed to get rid of the low quality reads. We still needed to align to a reference. The reference that we're using is the NC_063383.1. And I know there are several other references out there, but this seems to be the best one for our purposes. I know that there are monkeypox workflows out there that use primers, and so that's why I have the trim primers that are in parentheses. We're piloting using some primers from IDT for monkeypox sequencing, but those haven't been added to the Secret repo yet. And then we create a consensus with IVAR. which is really useful in that it easily puts in ends in the sequence where you don't have enough coverage. Since it is using IVAR though, you do have to be a little bit worried about indels and about what depth you use for consensus calling. But that was a similar issue with SARS-CoV-2 sequencing. And then if you have a monkeypox sequence, it takes that through next clade invader. And all of this is using the Docker containers of the StaPH-B workflow. You can either use Singularity or Docker with this. And so all you need to do to install in your environment is Nextflow and all of Nextflow's requirements, and then either Singularity or Docker and their respective requirements. And then you just need to make sure that your environment that you're running this on has enough computational power to run this. So if you use a kind of a high-end Mac, that should work. It should just take longer. But this should also work on the cloud, any kind of cloud that Nextflow will work on. This is how it would be run. This is also part of the StaPH-B toolkit. And the StaPH-B toolkit has a simplified command line structure. But it's basically Nextflow run, and then you give it the repo that it's looking for. And then you designate some kind of profile. I have a monkeypox profile. It is for metagenomic sequencing. And then the example is using Singularity to manage all the containers. And then setting the parameter of reads to the directory to where the paired end FASTQ files are. This does work with single reads as well, although I think that's more of an uncommon use case. And yes, so that's with metagenomics. For amplicon-based, right now there isn't a default amplicon-based monkeypox profile in secret, but you can add additional parameters for your custom application. Secret just needs a primer bed file, which is in reference to the reference that you're using. So if you're using a different reference than the NC underscore, whatever I said in the last slide, you have to provide the reference to whatever is with your primer bed, because otherwise the primers aren't going to match. And same with the amplicon bed. So the amplicon bed file is the bed file for what amplicons are being expected. And that can be generated from your primer file. And generally for the metagenomic workflow, the minimum depth is 10x. If you're doing amplicons, I suggest a higher minimum depth. I've listed 100 here. You're going to want something that gives you accuracy, but doesn't fail too many regions. And that's going to be largely dependent on what your amplicon scheme is and kind of what you're expecting for your depth for your samples. And then specify some sort of trimmer. Secret supports IVAR trimming or SAM tools amplicon clip. Other parameters worth mentioning, because Secret has over 84 parameters, and reading through all of them may be a little difficult to figure out which ones you may need to edit for your purposes. To clean the reads and remove low quality reads, you have the options of CKey clean or FASTP. For monkeypox sequencing, especially if you're doing a metagenomic where you have a large number of reads, I suggest StaPH-B because it is much, much faster than CKey-clean. The parameter filter being set to true, what that is that's a positive filter. And you'll get a paired end FASTQ reads of just those reads that align to your reference genome. And you could use those to then submit to the SRA. So we had a problem with our metagenomic sequencing that the NCBI, they provide the human read scrubber, but we were finding sequences in our reads that weren't necessarily monkeypox and they weren't necessarily human. And we were worried what would happen if other individuals found out what was in our sequencing that was kind of unintended, and we didn't want to really rock the boat. So that's one of those things that I recommend, especially if you're not doing amplicon sequencing. And there is this mark duplication. So there are some library prep protocols where you have baits for certain regions of the monkeypox genome, and then those are amplified up by PCR. If that's the library prep that you're using for your monkeypox sequencing, you definitely need to set this mark duplication parameter as true. If there's no PCR amplification, it's likely not going to do anything. If you're doing amplicon sequencing, then it's debatable as to whether or not you need it. If you're doing multiple sequence alignment, I recommend next align, although that does, with secret, that restricts what reference you can use for your multiple sequence alignment and phylogenetic analyses. Some primer schemes are really interesting, and SAMtools amplicon stats may have issues with it. So if you have a really interesting bed file, you may need to change the SAMtools amplicon stats options into something that will fit your primer scheme. And then if you need to use a different genome than the one that is the default, then you'll need to provide a reference genome and the corresponding GFF file, which you can download from NCBI. Another thing that's worth changing is right now the NextClade dataset default is human monkeypox, and for your analyses and your research questions and your purposes that may not fit your needs. And so changing that to an additional or a different NextClade dataset is supported. So future directions that are currently in the work is right now secret doesn't mask any of the repetitive regions, but hopefully when enough people email me back, I'll be able to have either a definitive list of what regions to mask or else provide some sort of options of which regions to mask. And I am hoping to include additional primer schemes and profiles. Something that I thought about including that I won't be able to include is there are some library prep protocols that are partial bait library prep and partial amplicon based library prep. And if that's something you want to work with, contact me and I can tell you how to do that. But that's not something that seems to be widespread. And since it is a little bit more intricate, I decided not to pursue that direction at the moment. And also, because there are tools out there for repetitive regions, such as like Lobster and Hipster, I was going to test those for some of the repetitive regions for monkeypox, and if they make it in, you guys will know about it. But otherwise, it's likely too ambitious at this point in time. And this is how you contact me. And there's the GitHub repo. And that's all I have to say.
All right, thank you so much, Erin. That was great. Okay, I know that we only have a few minutes left now for questions. I apologize. I always maybe pack these calls a little bit too tightly, but I think that there was a lot of amazing information that was shared by all of the people on the call today. And so I'm going to open it up for questions now. And yeah, I'll let people kind of go forward because I know that there were already some questions in the chat. And so if people who ask questions in the chat want to ask them, you can unmute yourselves and we'll go forward from there.
I did see a question in the chat from Young about like loading the sequencer and like how many samples. I have to say, so at Yale we have a genomics core with NovaSeq, so we don't load the sequencer ourselves. We can basically just tell them how many reads we want per sample. But I do see Luke from the Massachusetts Public Health Lab on the call. I don't know if you're there, Luke, and if you want to share some of your experiences with loading the MySeq at your place.
Yeah, I can talk really quickly. I actually messaged Byung directly, but for to answer questions for everyone, here we have been loading. We've been sequencing on the MySeq and using the V3 kits. We use the 600 kits, but we run 300 cycles, like the paired end, so 2 by 150. We also cap out our samples at 32, just based on the size of the genome, and we load at 12 picomolar. So, and if anybody has any questions, please feel free to contact us or Chantal or whomever. Thanks.
Looks like Curtis had a question in the chat for Erin. What was the bait capture kit that you were referring to?
Oh man, so I don't actually know or what company it was, or if it was just a hypothetical situation at that time. My apologies.
There isn't. So as far as I know, that the poxvirus group at CDC does have a set, but they have not been using it lately. Like it's when they actually want to go for samples which may have slightly higher CT values, but they are precious samples for whatever reason, because almost all monkeypox samples were rare to begin with. I wish it had stayed that way, but and the human component was also high. So I'm going to mess this up. The CT value for was lower. So that means you knew there was a lot of human, very little monkeypox in there. So when you're talking about 0.03% human monkeypox in there. So that's when they had that. I've seen some results. I don't think they really work for the current outbreak samples. You see a lot of gaps, so they would have to be redone, and they're extremely expensive. So it's not a way to go forward. So not quite hypothetical, but yeah.
All right.
Thank you. Appreciate it.
We have about 1 more minute left in the call proper. I did want to ask the speakers, are you able to stay on for maybe a few minutes in case there are other questions? Okay, awesome. I actually had a question, so maybe I'll ask it now. And for those of you who have to drop out the chat, this is recorded. So if you want to come back and see these, you can later. I'll post it up on the StaPH-B website. But so I had a question about what kind of hallmarks do you see during the rearrangements, and kind of what are some things to look out for if you're seeing those kind of like large rearrangements that would prompt you to then do some of the metagenomic sequencing.
Well, County Public Health Lab, they detected some discrepant results between various qPCR assays, where some of the clade-specific assays and generic assays had no detection, but they did have detection with the non-variola assay. Turned out after sequencing that there is this 600 nucleotide deletion that is causing the dropout, that they were able to pick up with the amplicon-based approach was confirmed with Sanger sequencing. I think that the caveat that we just want to put out there is that with short read sequencing, like you might miss some of these things. And that's why especially long read sequencing come in, because you can basically just cover like a larger area. Just to, like, I feel like it's kind of like, yes, you can do like high throughput amplicon sequencing, which is great for surveillance, but we should not just do one. You kind of need to keep your eyes open for things that you might miss with this approach. And that's why we kind of recommend doing some of the longer read sequencing in parallel.
Right. And I know Crystal Gigante and Minnesota Public Health and some of the others kind of did put out a preprint on the rearrangements that they found, and how many of you found that on the bioarchive. I'll try to find a link and send it. But those are happening in, which is why going back to de novo approaches, you would miss that even in the reference-based approach, because they were identical, like rearrangements and ITRs. Look at the paper, it's very comprehensive. So yeah, which is why we have been reluctant to switch to amplicon-based approach.
I just wanted to highlight again Michelle's question about the pass-fail. I don't know if Duwani, there's a perspective from the monkeypox sequencing group, or I think there's also an APHL monkeypox sequencing group as well. If there's been conversations of what is acceptable criteria of pass-fail, what should be utilized for, informing public
Again,
health
I'll go
action.
back to saying, like, in past, the monkeypox group would be lucky to say, oh, we have a 3x coverage, so should we keep it, or what, how? So those, we have gone back. It's been that way. In this current environment, the approaches are slightly different, but I think in our scenario, we are using 10x as a coverage cutoff for IVAR. If that helps. Overall, when the sample passes, I think it's more of like we are calling consensus. We're not using pass-fail at that level because you just don't know what other features might be there. It's when you are actually doing the analytics and you kind of see which regions are covered versus not kind of forms that. So whether that missing region has an impact on information content. Right?
Very fair. Yeah, thanks. And maybe, Michelle, we can work with other public health labs that are using this, and we can at least come around with, some kind of standard or like mean and standard deviation of what is expected when using these protocols, so that we can come like, is this the protocol, or is this potentially like a wet lab or tech or a lot kit agent failure kind of thing? So at least there's some kind of expectation of what kind of data should be.
Right. And the other thing is, like, we are using metagenomics approaches, right? So what our cutoffs would be different, because when you start getting into amplicon drop-offs, that's when you may have evidence for whether the primer set didn't perform well, or there's a genomic rearrangements that's causing, like, those are completely different issues now.
Yeah.
So you are talking about different, there's no one set way of doing this. Again, it goes back to what's the question you're asking and what's giving you enough information.
Looking in the chat, it seems that so Jennifer has a question that is CDC working on a monkeypox pipeline? And I guess maybe
yes, and our pipeline currently will be metagenomics oriented. Honestly, we are working. We are actually focusing more on the annotation submission pieces first. We're just trying to package them up so that it makes it easier once you have the consensus. It doesn't matter how you got there, right? That's one part. The other pieces would be, let's see how applicable they might be, but current focus has been on metagenomics because that's what we have we'll bring in, and maybe we won't have to work on the amplicon based one because you guys have done a great job between secret and other pipelines already. We'll just adapt it. I've been testing and knows.
I have a question to Duwani. This is Byung from New Jersey State Health Department.
Yeah. Hi.
We are doing some experimental monkeypox sequencing in-house. Previously, we've been sending out our specimen to CDC for the sequencing. And then there was a shipping issues, and then many of our samples got rejected because of during the shipment, dry ice have been thawed or something in that kind of issues. So we requested the CDC whether or not what would be the proper way to prove that our cells can do the sequencing in-house. That would be the good enough rather than sending every specimen to the CDC. And what would be the, is there some sort of guideline to the public health
Yeah.
laboratory?
This is where we're getting into, and I'll be honest, this is the most frustrating piece for me here is I wish I could answer this question, but a lot of people here have covered a lot of different approaches. We are doing straight up metagenomics, where we are essentially throwing away at least 80% of the reads, if not more. And in some cases, just monkeypox reads are 1%. And those use standard kits. The extraction is based off of our PCR diagnostics, so it's not long. It's one of those CLIA tests, so we get DNA extracted, which is extracted by PCR, which is what we get. That is what I can say what we are doing. I cannot say what we recommend. I cannot recommend anything.
Nice. Thank you for your answer, though.
All right, I have one more question too that may not have a good answer for this call, and maybe something that needs to be kind of talked about in the future. But Erin kind of mentioned it a little bit, and I know that Nick kind of mentioned it a little bit. And so I was just wondering, are there any masking approaches that people have used that have worked well? Is there kind of like a consensus in the community as to what is important in looking for like a masking model? And should we try to coalesce around something?
Those are excellent questions. And I would say, let's start with what reference everybody's going to use. I think that's an up and open question. Masking, there was a huge discussion on StaPH-B about 3 weeks ago, but strategies were suggested. I don't think there was a consensus. Maybe next year's we can revisit this topic. I'll put a try to tell Duncan to bring this up and see if we can get around that. Because I think even before we get to the masking question, the first thing is what is the reference that everybody's using?
That's true too. And it seems like there are a few that people have kind of coalesced around. So that may be something that we need to kind of come up with as a community before we can kind of answer some of those other questions. But it does kind of depend, you know, on what you're looking for too, right? Like what kind of reference you are using. I saw some
and yeah, I mean, I agree. I mean, some of the questions, and I always go back to this, and Logan, you know that, is like, we need to ask the questions we are trying to answer, right? Yeah. We need to know, and based on that, you take your analytics approaches. So you say you're gonna mask something. For a lot of people who are actually doing the analytics, I don't know if you saw the accordion preprint, they're talking about how the repeats seem to be expanding and contracting. So if you're masking out the repeats, you're losing that question. So it goes back to what are the differences you're looking at. And some of the differences on APOBAC3 are not just limited to non-repeat or regions. All of these are kind of coming into picture. Repeats do throw off the element. So before you get on to what the solution is, you need to know what the question is and what it's going to inform.
I think that, yeah, this is gonna, I wasn't expecting there to be, you know, like one answer on this call, but I did want to at least pose it out to the community. It looks like there were some other questions in the chat too. Byung, do you want to answer or ask your question?
I was just curious to the Yale group, whether or not they are planning to or currently working on improving the current primer sets to cover the amplicon dropout region.
Yeah, I'd say the current scheme is not like 100% perfect, but it is really good. So right now we're not really working on any changes. Those two amplicons that kind of drop out, like it's really like out of the bigger picture, like a very small portion that you miss. We did investigate, there's no primer mismatches, so it's probably something that you could potentially overcome by increasing primer concentration. But again, like overall, the results have been so good that we kind of are sticking with what we have right now.
Thank you so much. And since you brought it up on the chat box, so IDT is planning to release the pooled version of your primer sets, because I'm about to order through IDT.
Yes, they have been working on that for a while, and last thing they said is it would be like at least sort of the version that we would then have to validate would be available in a couple weeks, which would be around now. I just haven't heard. They kind of keep pushing it back. So only thing I can say, it is probably coming soon. I don't have an exact date for it. We still have some aliquots left, so if we can help labs, we still try to do it. We just cannot, promise everyone that we can send out many more of these aliquots. But if it helps you to bridge like a couple more weeks, then we're happy to help you.
Oh, that would be great. Thank you so much. I will contact you separately.
Sounds good.
All right, and it looks like kind of related to that question, there was another question in the chat. What is the best place to get the primers for amplicon-based sequencing using Libuit technology? And so I know some people have reached out to your lab in the past, but is that still an option?
It depends on how many requests we get. Like if it's a couple of requests, we can definitely help. In principle, anyone can just order the individual primers because they are in our protocol. And Nick can speak to this. It's just a lot of work to create pools by yourself. Like if you order like 163 pairs individually, it's a lot of pipetting fun. So that's why it makes a lot more sense if IDT were to create a pooled product, but that has just, been dragging along for a bit. So please feel free to reach out. We'll try to do whatever we can. I just cannot promise that we can. If we get overwhelmed with requests, we'll just try to help as many labs as we can.
Thank you. Yeah, pipetting fun is a nice way of putting it. I know that everybody has been so gracious in staying on for so much longer. So I wanted to make sure that we got all the questions. Were there any more questions that people had who are still on the call while we still have our speakers here? If not, then I'm going to go ahead and say thank you so much to everybody for being on this call. Yeah, this was a great talk. I'm so appreciative for you taking the time to be here and answer the questions afterwards and staying on past the allotted time. That was really, really, fantastic of you all, and our gratitude from this community to you.
Thanks for having us.
Thank you.